Hi, welcome. This module will look into exploratory data analysis, or EDA, and following up on what we covered in the last module, where we focused mostly on the spatial perspective alone, looking at mapping. Now we'll cover some traditional graphs, but more in a view of visual analytics, which I mentioned in the last module a little bit. And I've split this in two sets of slides. The first one, I'll cover some basic notions, again, some jargon, some vocabulary, get us all on the same page. Then I'll very quickly go over some basic statistical graphs, which you probably remember from high school, but just to make sure everybody's on the same page. And then I will focus a little bit on this concept of spatial heterogeneity that I alluded to earlier, but maybe it was a little abstract at the time, and in this section we'll make it concrete by means of specific graphical tools that we'll use to explore spatial heterogeneity. So first, some evolution. Exploratory data analysis is actually very interesting. It started in the late 60s, early 70s of the previous century by a group of statisticians, primarily at Bell Labs, who were getting very frustrated at two things, actually. In applied work, modeling without looking at the data, so right away getting into the statistical modeling, regression analysis, things of that nature, ANOVA, but also in the statistics profession as a whole, the focus on mathematics, on proofs, on theorems. And this is a similar frustration that we saw earlier on with the advent of data science. So these were people who were working on big research problems, and especially, as I mentioned, at Bell Labs, looking at issues of quality assurance or managing telecom networks and things like that. And John Tukey came out with this book on exploratory data analysis in 1977, wherein he introduced, or basically I should say, looked at in more depth some graphics and devices, as we call them, by which we can understand the characteristics of underlying distributions of the data. And then there's a lot of controversy about exploratory data analysis because it's not cut and dry. Like, the statistics you're probably familiar with. You have a null hypothesis, you have a test, you reject the null hypothesis, you have a p-value. Everything is always the same. In exploring data, which we've already seen a little bit when we talked about geovisualization, it's as much an art as a science. Of course, the devices, the tools are all based on solid methodology, but how you apply those is actually, a lot of it is learning by doing, and you have to go at this quite a few times before you really get comfortable at it. And I.J. Good, in an article in the journal Philosophy of Science, it's actually, if you have the time, it's a great piece to read and to think about what exactly is exploratory data analysis and how is it different from standard statistics. And he used the term discover potentially explicable patterns. And it's very important in here, this notion that you're not actually explaining anything, you are discovering things that might be explainable, which is a little bit different from what we usually do. And so here's a sense of what this is: the cover of the Tukey book, and then the article. As I said, if you have time, it's a good read. And so out of this movement for more attention to looking at the data and understanding from looking at the data what is actually going on, is this notion of visual explanation. And some of it, so this early move came out of the statistics community, and then visual explanations, some of it came out of the design community. In the work by Tufte, he has a number of books where and he even has short courses where he tells people how to do proper design, how to design analytical graphics, basically. How do you get a certain meaning portrayed by the design of the graphic. This is a little bit different from visual analytics, which we alluded to in the last module as well. Remember to detect the expected and discover the unexpected, where it's all about interacting with the graphics, interacting through different types of visual interfaces. So Tufte is really about presentation of a result, so that the result is meaningful and you understand what's going on and you put all the different relationships together in the graphic, whereas visual analytics is more about how do you use these different analytics in a progression in the process of learning from data. So it's a learning process. This is an example that Tufte and many others often use. There are two classic maps by this French cartographer, Charles-Joseph Minard, and the one on the top is the route from Hannibal as he crossed the Alps and invaded the Roman Empire. And the most famous one is, and many of you might know this, is the one on the bottom, and it's basically the route of Napoleon as Napoleon first moves into Russia and then gets defeated and moves back from Russia. And what is very interesting about this graphic and why Tufte and others like it so much is that it combines so many different measures in one ensemble, if you wish. So first of all, the thickness of this branch, if you wish, is the number of soldiers in the army. So as the battles go on, the number declines, and then on the way back, you see the effects of the cold winter and how that reflects in the number of soldiers. And this is highlighted by a graphic in the bottom as well. So there's different graphical elements. They are tied together in order to explain a statistical process. And a lot of that in modern technology has become implemented through graphics in a computer screen. So as I mentioned in the other module, my view of exploratory spatial data analysis, so not just EDA but ESDA, is going beyond simple EDA by spatializing the ADA, making the EDA special in the form of taking into account explicitly the spatial information. So the spatial becomes an integral part, an essential part of the data exploration. And the focus is not just on any patterns, remember the potentially explicable patterns, but on spatial patterns, obviously. The kind of things we will do, and this is pretty much what we will be doing in this course, is we started with this already, describing spatial distributions. We covered dynamic maps, and today we'll cover dynamic graphics from the non-mapping kind. We identify atypical spatial observations. We saw in the previous module these outlier maps, the box map, for example, percentile map, that allowed us to see where outliers are. Later on, in later modules, we'll deal with local spatial autocorrelation, which is yet another way to identify spatial outliers. And then we focus on the two core spatial effects: spatial dependence, or spatial autocorrelation, and spatial heterogeneity. Today we'll focus on the latter, on spatial heterogeneity. In later modules we'll switch to spatial autocorrelation. So what is this about? Finding clusters, hotspots, cold spots, structural breaks, that's the heterogeneity, and then regions in the data, which we'll cover in the other course, the spring course that I mentioned earlier. So that's pretty much what we're going to be doing. And a core aspect of this is this notion of a view. And this is how data visualization is operationalized. Basically, you think of a graphical representation of the data, and that could be a simple table, a list, a graph, or a map. And the key behind effective data visualization is a combination of all these views. So all these different views are tied together and in a dynamic framework. And the different views are manipulated. So the analyst, you, becomes an integral part of the whole process. You interact with the data. So basically what that means is you pick which kind of views are good to represent the data. You move them around, you focus in, you link, you rearrange them so that these graphics become a tool in the exploration of the data. And in the last module, we talked about the aha moment, the way, the process of interacting with the data where you find unexpected things all of a sudden. Well, this is all the same thing. It's a bit, the previous version was spatial, this is not. Key concepts in this, and I alluded to this a little bit already in the last module, but this is fundamental to dynamic graphics and dynamic data exploration, is the concept of linking and brushing. And in fact, the whole architecture of GeoDa is built on top of linking and brushing. So there's two concepts. The one is a dynamic version of the other one. Linking is the simple idea that if you select something in one view of the data, so this view is a table, is a graphic, is a map, then that observation or that subset of observations is immediately also selected in all the other views. So if you've done some GIS before, you might have seen a simple version of this. If you click on an observation line in a table, you will see it highlighted in a map, or vice versa. We saw early on in the early lab notes, we saw the use of the selection tool in GeoDa. Once you select in one view, it's also selected in all the other ones. Then brushing is a dynamic version of this in the following sense. So when you have a selection, it's linked to all the other views, but if you change the selection in the other views is also immediately updated. So literally you design something, and there's more examples of this in the lab notes. You design a rectangle around some observations and you start moving it around. And as you move it around, obviously the selection in your current view changes, but then the corresponding selection in all the other views also gets updated immediately. That's the concept of brushing. So linking and brushing are critical to the implementation of dynamic graphics. So a lot of what we'll see in as specialized graphics as we move on has under the hood this linking and brushing implemented, and we'll exploit it in particular in a few minutes when we look at spatial heterogeneity. So basically this exploratory spatial data analysis uses a lot of ideas from EDA, pioneered by Tukey, transformed, morphed into visual analytics, dynamic graphics, using linking and brushing. So now, as I said, I figure many of you have had this stuff in high school, but maybe it's been a while. Just some basic univariate and bivariate graphs. So the univariate ones, the main purpose of these is to describe the distribution of the data. And in fact, in the previous module, we talked about the box plot, which was a box map, I should say, which was a special version of a box plot. And that's the same idea. I'll briefly repeat the box plot here. Histogram, very straightforward, probably the most used tool to describe a univariate distribution. And then when we talk about two variables, we're so far primarily interested in linear association, and then we look at the scatter plot. We'll also see how that can be pushed a little further and look at nonlinear associations. So this is probably just a refresher for everybody, making sure we're all on the same page. Histogram. What's special about the histogram? That it is a discrete representation of a continuous variable. So the histogram, has a number of bars. This is not the same as a bar chart, because the height of the bar is the proportion of observations that are within the range on the horizontal axis. So there are two critical parameters. In fact, one is the flip side of the other. You either pick the number of bins, and then the range, which is the difference between the minimum and the maximum, gets divided by the number of bins, and that determines the width of the bin. So say 5 bins, these are 55 observations going from 8.4 to 55.4, and then 1/5 of that determines the size of the bin. And so then you basically get these cut points, and then whatever observation is in a particular interval determines the height of the bar for that interval. So that is one way to approach this. Another way to approach it is to set the bin width. So then you either set the number of bins, which determines how wide they are, or you set the width of the bin, which then determines how many bins there are. So one is the flip side of the other. One aspect to keep in mind, in the end, this is a discrete representation of a continuous distribution. So it's very similar. We talked about this in the previous module as well. It's very similar to the way you define the categories, the classifications for a choropleth map. Choropleth map is also a discrete representation, but of a spatial distribution of a single variable. So histogram, we should all know this. Box plot, I talked about in the previous module in the context of the box map. So the box plot is a representation of the distribution where all the data are sorted from low to high, and it focuses on the median rather than the mean, the quartiles, and then it has this interesting notion of outliers that we saw last time. So just to refresh your memory, here's a box plot. This is the median. First quartile is here, third quartile is there. The interquartile range determines how far up this fence is. So in the default case, it's 1.5. All these observations are outliers, and these observations are outliers. Or you can do 3 times the interquartile range, and then the fence is up here. We no longer have a lower outlier, but we still have some upper outliers. So this should be familiar by now. Histogram, box plot, simple graphs. Scatter plot, still simple. 2 variables, 2 axes. So every observation has what is called a tuple, so has a value for each of the variables. And so it's represented as a point. Every observation is represented as a point in a 2-dimensional graph, in a 2-dimensional space. And then to simplify the scatter. So the scatter plot is very useful for small to medium-sized data sets. When you have lots and lots of data, basically your scatter plot becomes one big blob of points, and it's actually not that useful to see anything in it as such. But then we resort to what is called smoothing of the scatter plot, which is a way to bring out the general pattern, the general trend. The traditional, the easiest way of smoothing is just a linear fit, a linear regression line, which gives you an intercept and a slope as a summary of a data. But there's also a way to do a nonlinear smoothing by means of a local regression analysis. And this is called lowest or lowest, very confusing, which is which, but basically the same idea, only the implementation is slightly different between them, which is a very technical matter. But just to give an example, this is a simple, from our New York data set, simple 2 axes. Every point is an observation. The linear fit gives the overall trend through the data. I'm assuming everybody's familiar with this. Then the nonlinear smoother you may not be familiar with. So basically, a linear regression takes all the data and fits one fit to all the data. A local regression takes a subset of the data, and it's the same idea. You get a fit, you get a slope, but that slope is computed by a small range around each point on the x-axis. This smoothing works really well in 2 dimensions, not so well in higher dimensions. But in 2 dimensions, you can think of it as making a little interval around each observation point and then getting a slope from that. And then this interval gets moved over, and each time you get a new slope, and then you kind of connect them together to get the overall choice of the curve. So it uses a subset of the observations. How wide that subset is a very critical concept, is a concept of a bandwidth. And the larger the bandwidth, the smoother the curve. In the extreme, the bandwidth will be taking all the observations, and then the nonlinear smoother will approximate a linear fit. It won't be exactly a linear fit. That depends on the method that's used. Some methods downweigh observations as they are further away from the focal point, kind of like a kernel logic. We'll probably talk about that later on some more in this course. But you can think of a kernel logic as giving lower weight to the data points that are further away. And so as a result of that, it's not going to be exactly a linear curve, but that's the idea. So the idea is you take a subset of the data and then you kind of move it over. Let me show you. So here, to think about this is, let's say we start with this data point and we take a range around it, and then we compute a fit for this subset of data, and then we move it over and then do it again. Now this is the default case in GeoDa, which uses a bandwidth of 1/5 of the range. So if this is the range on the x-axis, so 1/5 would be about something like this. So you take this area, you get your fit, and each time you move over a little bit and you adjust the fit. And the result is something like this, where you see an increasing curve, then a little bit squiggly, more or less flattish, and then a very steep increase, which is quite a different impression from the uniform fixed slope that you have in the traditional linear regression line. So that's the whole point of the local regression, of the smoothing, is that by focusing on subsets of the data, you pick out local patterns. So if all the patterns are basically the same, your nonlinear smoother will be very similar to your linear fit. But if you have, say, structural breaks in the data, and this is brought out even better when we increase the bandwidth. This shortens the bandwidth. You see what happens. It gets very spiky. It picks up very local phenomena in the data, often not that useful. But here's the opposite, where I increase the bandwidth to 40% of the data. So now instead of 1/5, it's 2/5 of the data. And now you get more of an overall pattern. And I would suggest that this might imply that there is this kind of almost linear progression here, and then we reach this kind of critical point around 40% of families with children, and then all of a sudden the slope kicks up and goes up. And so this would suggest the existence of a structural break in the data. So the one of the effective uses of this lowest smoother is to look for structural breaks in the data, or subsets of the data where a different linear association may hold between the data. So here we have a suggestion that maybe we have this slope in this first part of the data and then the other slope in the other part of the data. And when we talk about multivariate associations, you'll see that we use very much the same kind of logic, is looking at subsets in the data and really assessing whether the same relationships, the same distributions hold in all the subsets of the data. And this is brought out even more when we focus explicitly on spatial heterogeneity. So as I've mentioned a couple of times now, we're interested in spatial effects. Spatial effects are twofold. Spatial dependence is one thing, spatial heterogeneity is another thing. And what is spatial heterogeneity? It's basically looking for structural breaks. The characteristic that we're interested in is structural breaks that have a spatial imprint. And specifically, we're looking for different spatial subregions in the data, spatial subsets of the data, where there may be differences in the statistical phenomenon that we're interested in. So what could that be? Different distributions in different subregions. For example, we're interested in characteristics of this distribution, like a mean or a median. For example, different parts of the city, do they have the same median house price, or are house prices higher in one part of the city than another part? That is a classic application of looking for spatial heterogeneity. So that's just kind of the overall distribution, whether that distribution is the same. If we look more specifically at the association between two variables, then we might be interested in the extent to which the slope of the regression line is different between different spatial subsets of the data. Recall our lowest smoother, we had one slope and then another steeper slope. Now, what if these two slopes corresponded to two spatial subsets of the data? Say one subregion has the flat slope, another subregion has the steep slope. I mean, the scatter plot as such cannot tell us that. It's similar to what we talked about earlier about the difference between non-spatial analysis and spatial analysis. A box plot, as we've seen, can identify outliers, but it doesn't know where these outliers are. Similarly, the structural break suggested by our lowest fit suggests that there is a break, but it doesn't tell us where this break is. Spatial heterogeneity is about making this spatially explicit. And let me illustrate this with two particular tools that are present in GeoDa. One is, we call it an averages chart. It's really designed to do pre and post analysis, looking at the difference in means, specifically with a focus on policy analysis. Let's say, classic example is the introduction of seatbelts. Is the number of car deaths before and after significantly affected by the introduction of seatbelts? And there's many other policy applications where you cannot do randomized controlled trials, but you have economists like to talk about natural experiments and things of that nature. So basically, what we're focusing on here is, are the means in two subsets of the data the same or different? So the point of departure, the null hypothesis, is that they're the same. We're trying to reject that null hypothesis. What is different about it, and different from standard practice, is that the subsets are spatially determined. And so by means of some spatial selection mechanism, say brushing in a map, which we've seen before, we determine which part of the data is selected and the complement is not selected. Now, many of you may be familiar with t-tests and some other flavors of tests on differences between means or differences between medians. Here, in this particular tool, we use a slightly different approach because it's all in function of setting up a dummy variable regression where we have a baseline and then a dummy for the selected. So we're interested in finding out whether the coefficient of that dummy is significant, and one way to do that is through the F statistic of the overall regression. So if you haven't had regression analysis, it's no big deal. It's just one way of assessing whether the slope, which in this case is just a bump because it's a 1 or a 0. When it's 1, it's the selected. When it's 0, it's not selected. So it shows what difference in the mean there might be between the two subsets. And the average chart has a number of different components. First of all, you have to set up the selection, and we do that by means of a brushing or selection in the map. In this particular example, we're looking at rents, and we have selected 10 neighborhoods in Manhattan out of the 55, so the 45 are the other ones. The median rent is almost double in Manhattan from the rest. We see that on this little graph here. The black bar is the overall mean, the red bar is the mean in Manhattan, and the blue bar is the mean in the rest. So then really the question is the red value different from the blue value? Now you might say, well, obviously, but it's actually not that obvious because it depends on and those of you who've done some statistics before will know this, it all depends on the variance within each of the groups. So we run this little test here, and in this case, indeed, clearly it is different, right? So what is special about this is just a difference in means test. What is special is that the selection of the subsets of the data for which we're interested, whether the means are the same or different, that is spatially based. So that is what is the main differentiating factor here. And then the other way to address the second type of spatial heterogeneity, where we're interested in the slope, is through brushing the scatter plot. Now, brushing the scatter plot is a very old technique, and its early implementation was completely aspatial. So the idea was, what happens in the slope with the slope in a scatter plot if we change the subset of the data for which it is fit? So ideally, if the relationship is really stable, it shouldn't matter. No matter what subset of the data you take, you should always get the same slope. But if there is instability in the relationship, then you'll see the slope switch around. And so basically, you select a rectangle as the brush, and then you move that brush over the scatter plot, and you assess whether the slopes stay the same or vary. So that, in the literature, initially that was called dynamic brushing, and the way we implement it in GeoDa is that we recalculate the slope on the fly. Now, what makes it spatial is that the selection is actually driven by the selection somewhere else. So because we select in a map, through the linking process, that selection is evidenced in the scatter plot. As we change the selection in the map, the selection in the scatter plot is updated, and the slopes are recomputed, and we actually carry out a formal test. So here's the idea. We have our brush, and you grab the brush, and you'll see more illustrations of this in the lab notes, and you just move it over the data. And as you move it over the data, you have the red points, the selected points, with their regression line. In this particular case, it illustrates a subset of the data where there is no relationship whatsoever between these two variables. The line is flat. And then the complement are the blue ones with their regression line, and the purple one is the original regression line. So as I mentioned, what we're interested in is a little more formal test, and this is one of the very few times that we carry out a formal test rather than exploring is we have these three slopes: the overall, selected, unselected. The null hypothesis, the point of departure, the thesis that we want to reject, is that the slopes are the same. So we have no a priori reason to suspect that these slopes might be different. So point of departure, they're the same. We take a subset of the data, recompute the slopes on the fly, and then carry out what is called a Chow test on the constancy of the coefficients. And in essence, a Chow test compares the fit of the two subsets to the overall fit. And if there is no structural break, then the sum of the fits of the subsets should basically be the same as the overall fit. If there is a structural break, then the overall fit is missing something, and so therefore there will be a difference with the fit of the subsets. So the formal derivation is given in the lab notes. That's not really the point of this course, but we use it as a quick and dirty test on spatial heterogeneity. So why is it spatial heterogeneity? Because the selection is spatially defined. So typically brushing in a map. So then we have this kind of phenomena as we're brushing in the map. So the selection is updated. As the selection is updated, we get a regression result for the selected, a regression result for the unselected, and then the results of a f-test on the that which is what the Chow test is, the null hypothesis of equal slopes. Now, in this case, you don't really need a test. One is positive, the other one is negative, but that's confirmed by a very small p-value. So that's the idea behind dynamic linking and brushing to look at spatial heterogeneity. So what we've done in this first part is basically refresh some notions, some concepts of visual analytics, exploratory data analysis, dynamic graphics, the critical notions of linking and brushing, which allow us to visually explore patterns in the data. I quickly went over some standard graphics that I'm assuming everybody is very familiar with: histogram, box plot, and a scatter plot. Then maybe something you're not so familiar with is a nonlinear smoothing of the scatter plot, which allows you to look for potential structural breaks or other nonlinearities in the data. For example, is it an inverse U shape or something like that? And then finally, we began to address this notion of spatial heterogeneity, which is just like any other heterogeneity, except that the subsets of the data on which the analysis is based are spatially determined. So in practice, this is implemented by brushing a map and then looking either at the differences between the means in the two subsets or looking at the changes in the slope of a regression line and testing equality by means of a Chow test. So that's the first part of looking at classic exploratory data analysis.